Wait a minute, I need to pick up something at the front. Okay, so I hope we're starting now. All right, any questions? No. All right, first of all, there are many ways of looking at spinning statistics. The one simple way of looking at it is one I'll describe now. It's not by any means a full proof. So, I'm thinking that A and M and B and M are two eigenstates of Jz. So let's see. And to follow the de Blasio rule, I'm going to say a few things about spin statistics. First. And so suppose there are 2 points. Let us say one is Tx 0, 0, and the other one is T minus x 0, 0. And we do a rotation about the origin by pi. So such a rotation will be represented by a unitary operator, and u on am will be e to the minus I m pi am, and on the other hand, u on b m will be e to the minus I m pi bm, and consequently bm u inverse or u adjoint will be e to the I m pi b. Yeah, okay. So now, if we have a field that has well, let's see. If remember this, I'm going to be thinking mainly of spin 1/2. But remember, the general field is a J prime field, but the under rotations, the J0 field behaves the same way as the 0J field. And so in general, under rotations, U of R general field, let us say Jm. Well, let me use L instead of M here because we've got M there. On T and X, U inverse of R. And now I'm thinking of, again, a rotation about the z-axis of angle pi, just as this was that. Then this will be I mean, if it's actually a JJ prime field, then this will be e to the I pi, well, it would actually then be L prime, wouldn't it be? So it would be e to the I pi L plus L prime if it was a JJ prime field, and we're looking at indices LL prime, and they don't change. So this would be psi J prime, L prime, and now it would be T minus X. And so let's simplify the notation a little bit and write this as U of R psi L Tx U inverse is, I'm taking, well, let's see, what did I call it? I called it L. All right, let me add. All right, I'm going to call this M prime. This would be M plus M prime. This eraser produces more white than the chalk. M plus M prime. And now I'm just setting L equal to M plus M prime. Okay, all right. And for practical purposes, we're considering the case L equals a half. Or minus a half. So then what we get is then e to the I pi, did I call it L? Yes. And this, I'm going to use a different eraser. Well, just a span. Okay, so the thing just requires a factor of L, where L is the sum of those two indices. And for practical purposes here, L will either be 0 or 1, or 1/2, or minus 1/2. So now what I want to do is have here Bm psi L of Tx psi L of T and minus x Am. And now I'm going to insert Bm U dagger U and or U inverse U rather. And so this will be U inverse U psi L of Tx U inverse U psi L of T minus x U inverse U Am. Now U on Am is equal to minus I pi M. U inverse on Bm is equal to I pi Bm. So those two cancel, and we get Bm U psi L Tx U inverse U psi L T minus x U inverse Am. And now this gives us, each of these will get e to the I pi L, so we get e to the 2 pi I L Bm psi L T minus x psi L Tx Am. And so what we get then is that Bm psi L of Tx psi L of T minus x plus, no, minus e to the 2 pi I L is times psi L T minus x psi L Tx Am. The sum of these two is 0. Okay, so for L equals 0, you see this says that spin 0 fields should commute. For L equals a half, this is e to the I pi, that's minus 1. You get that a spin 1/2 fields should anti-commute. And at space-like separations we're talking here. On the other hand, if you go to L equals 1, you just have e to the 2 pi I, that's just 1. You again have that the fields should commute. Now, the thing in this that is a shortcoming of this argument is that I've assumed m equals m. Suppose this were m equals m prime. Well, then those phases wouldn't have canceled. And that's why this isn't really a proof of spin in statistics. But it's a suggestion of spin in statistics. I'm not sure that, well, enough said about that. Now I want to go to say some words about energy. These are, here, the de Blasio law. Now, energy, and there are two aspects of this. One is the connection with spin in statistics. And the second one is basically the divergences of quantum field theory. And in fact, this is the worst divergence of quantum field theory, and that I know. And thirdly, just a word about supersymmetry. Most people who talk about supersymmetry avoid mentioning this divergence, and instead say that the Higgs mass is unstable, as our colloquium speaker did. But the instability of the Higgs mass is related to a quadratic divergence. These divergences are quartic, so they're much worse. And the best thing, in my view, the real promise of supersymmetry was a sort of natural cancellation of infinities. But on the other hand, so far there has been, I must have told you guys this. I once was at spent a summer at Berkeley, spent a couple of summers at Berkeley, and there was a sign on the bulletin board announcing a conference, and it was called Supersymmetry Confronts Experiment. And someone had written on the announcement, Experiment 10, Supersymmetry 0. Because that was many years ago, several decades ago. The score is probably Experiment 100, Supersymmetry 0. On the other hand, there's a lot of dark matter out there, so maybe the superpartners are, well, it wouldn't do to say the superpartners are dark because the superpartners and the partners interact. It's hard to. Anyway, enough said about that. Okay, having satisfied the de Blasio rule in a minimal fashion, let's look at a scale field with an action density d mu phi star, d mu phi minus m squared phi star phi, and we've looked at this field several times. The stress energy tensor, or the energy momentum tensor, whatever it's called, it's partial L, partial d mu phi, d nu phi, plus partial L. This is essentially just a complex conjugate. D mu phi star, d nu phi star, minus g mu nu L. I'm just going to write this as L. It's too hard to type math now. And so this is d mu phi star, d nu phi, plus d mu phi, d nu phi star, minus g mu nu, and now d mu phi, d mu. Well, this should be an alpha. Okay, so that's the energy momentum tensor, and the component that's the energy density is T00. We can write this as script D for energy density, and it's T0 phi star, d0 phi plus grad phi star dot grad phi plus m squared phi star phi. So that's a eminently reasonable positive definite expression, at least positive. Any questions? All right. So now, if we write the field phi, by the way, my plan today is to finish chapter 12. I won't cover every phrase, and you guys can read it. I think there's a certain amount of hand-waving in chapter 12. There's also a very serious typo, which, however, is in the typo list that Schwartz put on the web. So what was I going to say? Yeah, so I want to finish 12 today. So that's where we're going. Blasio's. All right, integral d cubed p 2 pi cubed, the square root 2 omega p. Remember, omega p is just square root of m squared plus p squared. And then I'm just going to use, today I'm pretty much going to use Schwartz's notation rather than the more elaborate Weinberg notation. Okay, so that's the field, and now if we ask what the energy is, well, of course, it's an integral of over space of the energy density, T00. So E is an integral. And this is an integral d cubed x. So we have, of course, d cubed cubed, d cubed, what's the other one? P 2 pi cubed, 2 pi cubed, 1 over square root of 2 omega p, 2 omega q. All right, now we've got a big expression here. And you can imagine if you do time derivatives, you pull down a p0, you do a space derivative, you pull down a vector component of p vector. And altogether, what happens is this. You get minus omega q omega p plus q dot p. These are three vectors now. AQ dagger e to the I qx minus BQ e to the minus I qx times minus AP e to the minus IPX plus BP dagger e to the IPX. Okay. That, and then there's the mass term, which is actually simpler, namely m squared aq dagger e to the iqx plus bq e to the minus iqx, and then ap e to the minus iqx plus bp dagger e to the iqx. Okay, right bracket. All right, now, if we've kept all this straight, then let's see, you might wonder why we have a relative minus sign here. Of course, the relative minus sign reflects the relative minus sign up here. Anyway, I'd encourage you to actually, it wouldn't hurt for you to go through this calculation on your own and verify that I haven't screwed up too much. In any event, what we get is this. What we get is that the energy is an integral dqp 2 pi cubed omega p, that's comforting, ap dagger ap, and then there's the oops term. It's bp dagger. Okay, the things are in the wrong order. Now, we sort of have two choices. We can say, well, let's apply, this is a spin zero field, so the operator should commute. Well, commute modulo, satisfy commutation relations. And in fact, if we do then apply the normal commutation relations, it would be BP dagger would be equal to BP dagger BP. In other words, no change. But what is just an IH bar in ordinary quantum mechanics becomes 2 pi cubed, or a delta ij in multi-particle quantum mechanics and many variable quantum mechanics. This is d cubed of the zero vector because it's the two p's are identical. It would have been p minus, excuse me, p prime. And of course, Dirac lets us write a delta function as an integral over all space of 1 over 2 pi cubed phase factor. But when the argument is 0, the phase factor is 1. And so this is actually BP dagger BP plus the volume of the universe, which is a big number. And so what we actually get then is that this is equal to integral dqp 2 pi cubed AP dagger AP plus BP dagger BP, and this just counts the number of quanta of each kind in each momentum. And of course I left out the energy, which is what we're talking about, omega p. And then there's another term, and the other term is V, integral dqp, omega p over 2 pi cubed. Okay. So this, this last term is quartically divergent because it's d cubed p, and omega p is the square root of p squared, essentially, for large p. And it's even worse because you multiply it by the volume of the universe, so it's a very big number. But even as an energy density, it's quartically divergent. Okay. Now, in fact, precision cosmology measurements tell us that there is a small energy density to empty space. But it's small, it's millivolts to the 4th power or something, and it's not infinity to the 4th power. Okay. So that's what we get. The term we like, and then this awkward piece. And of course, in the standard way of dealing with this is to say, well, this Lagrangian here, I mean, we picked it up off the street. We didn't know what it was. We're going to subtract L. All right. So let's add, what was it? Infinity to the 4th power. Okay. So then, when we subtract L, subtract Z00 L, it'll go away. And that's the standard way of handling this. But of course, if that's the way you treat the energy density of the vacuum, you're hardly going to be able to compute our energy. All right, but there's another lesson here. And the other lesson here is the spin statistics aspect. Namely, suppose we had chosen to have these operators anti-commute rather than commute. Well, then we would have had a minus sign here. And what we would have gotten was the same thing, but a minus sign there. And that would have told us that, so let me put this in parentheses, from that would have been really dreadful, because it would have said that you could go down in energy by creating large numbers of antiparticles, and if the antiparticles don't carry any conserved quantum number, then you'd have the universe would just go, and we'd all be blinded by a flash of radiation from all these antiparticles that would be created. All right, any questions? So now we're going to do the fermion part. Oh, Susie. Yeah, we can't get to the Susie part yet. Let's do the fermion part. Now, one of the things about fermions, there's no end to trouble with fermions. So what we're going to do here, instead of deriving, it's actually, I think, a fault of the way we teach physics. When we teach mechanics, of course we do non-relativistic mechanics, and then at the very end we say, well, high speed, we have to do special relativity. And moreover, there are no constraints in most of the mechanics that we teach. And in fact, in gauge theories, there are constraints, namely Gauss's law, and there are 4 constraints in general relativity. Anyway, so what's T mu nu in this case? One of the awkward things about fermions is that even deriving the Dirac equation from Lagrangian is not a trivial matter. Deriving the Hamiltonian from the Lagrangian is not trivial. Everything is kind of confusing. And there are actually constraints built in here. Dirac wrote a couple of books about that, and of course he always followed George Orwell's advice on writing English, namely if you can yank a word out of a sentence without changing it, yank out the word. So his books are very thin. On the other hand, they're pretty dense. Sorry for laughing so much. All right, this is gamma mu d nu psi minus g mu nu. Let's do it this way. Well, actually, we don't even need that parenthesis, so let me get erase. Okay, so that's our T mu nu. The energy density, which is T00 in this case, is psi bar I gamma dot grad plus m psi. And remember, when we're dealing with the energy density, we've already used Noether's theorem to get the conserved current, and that relies on the equations of motion. So we can always use the equations of motion here. And when we do, what we find is this is I psi bar gamma 0 psi dot, which equivalently is I psi dagger psi dot. Okay, so these are 2 different ways of writing it. Okay, so now we're going to evaluate this and see what we get. Any questions? All right, so the energy integral dq dx of 0, this is an overall I, of course. Integral dq dx, integral dq, what is it, q, 2 pi cubed, 1 over the square root of 2 omega q, integral dq p, 2 pi cubed, square root of 2 omega p, sum on s and s prime, e to the I px, and then we have a dagger of p and s prime u of p and s prime dagger plus e to the minus I of px and b of p and s prime v dagger of p and s prime, and then this multiplies. Maybe I should just go to the ring. Well, time derivative. Put in the parentheses too soon. Time derivative e to the minus I qx a of q and s u of q and s plus e to the I qx e dagger of q and s e of q and s. All right, close parentheses. Okay, well, of course, Dirac saves us again because it's an integral d cubed x, and so that's going to, and everything that has a phase factor, p dot x or q dot x. So what we're going to have is delta of p minus q, delta of p plus q. Those are the two forms we're going to get. And for u and u dagger u, v dagger v, these terms are going to have the nice delta function. On the other hand, u dagger v and v dagger u, these are going to have the delta function of p plus q. On the other hand, and that would, so we would have things like this. We would have u dagger u of the same, in other words, we would have u dagger of p and s, u of, let us say, q and s prime, and so this will be delta cubed of p minus q delta, well, I'm sorry, that's not a delta, this is just, this would the delta functions of this force q equal to p, so we have a p, and this is 2e delta ss prime. And these ones give us u dagger of p and s, v of p and s prime, and that's just 0. And the other one, v dagger u, is also 0. Okay. So there's a certain amount of simplicity that occurs here. And so if we keep the arithmetic straight, what we wind up with is that this is the sum over s from minus a half to plus a half. Integral d cubed q, 2 pi cubed, omega p. And then what we have is very nice. It's a dagger of p and s, a of p and s, and then minus b of p and s, b dagger of p and s, minus b. And the first physicists who computed this back in, I guess, the 20s somewhere, were kind of worried because they saw this term here and they didn't know about anti-commutation relations at first, and so they thought, oh God, this is really terrible. But I don't know if it was Dirac, perhaps, who straightened them out. But anyway, they figured out that, in fact, minus b of p and s, b dagger of p and s, should be b dagger of p and s, b of p and s, and the term is minus v. So in other words, we put this on this side. In other, this is the same thing as the anti-commutator b of p and s, b dagger of p prime s prime equals 2 pi cubed delta p minus p prime delta s s prime. So that's what we're talking, that's the actual relation, and that gives us then this. And so what we have is that the energy is sum over s integral d cubed omega cube 2 pi cubed, and then it's a dag of p and s, a of p and s, plus b dag of p and s, b p and s. Then, and then minus sum over spins, volume of the universe, integral d cubed q, omega q over 2 pi cubed. Okay, this is, of course, the 0-point energy, as was the other one, that's what people call it. And it's quartically divergent, but it's a minus, it comes in with a minus sign. So that's where, that's some of the promise of supersymmetry. Namely, if you just have this, you can even have highly broken supersymmetry. In other words, if the supersymmetry is so broken that the masses are just all scattered about, but there are the same numbers of Bose modes as Fermion modes, then all these quartic divergences cancel. Because the quartic divergence doesn't care about the mass. It's just a piece, it's just d cubed q q. And then the mass term controls a quadratic divergence. So, so the worst divergence of quantum field would go away if you just have, you forget supersymmetry, if you just have the same number of Bose modes as Fermion modes. Now whether that could very possibly be true. Anyway, if instead we had used commutation relations, well then what would have happened is we would have turned, we would have gotten, let's see, where did we start here? We would have gotten, I just want to try to get things in the right order. Well, we would have called that b dagger commutator equals something or other with a delta function, let us say. And so this would have been b dagger minus b dagger b equals something big. And we started out with this, yeah. So this, let me try to get this straight. We had the commutation relation would have this. What we wound up with was, yeah, before we get the, all right, I'm afraid that I skipped a line here, skipped E. What you wind up with is this from that calculation. And so if you are saying what is minus b dagger, then it's b dagger b minus v, which is the thing that I wrote down, namely this. But if on the other hand you use commutation relations, then you have minus b dagger is minus b dagger b. Then you get, again, negative energy, but you have, the energy gets lower the more antiparticles you make. And again, if they didn't carry a conserved charge, then it would be really nuts. Because the fact is that of these fundamental fermions, most of them are charged and do carry a conserved charge, carry electric charge. Okay, so there's some reason to hope that that the some symmetry that gives us the same number of Bose modes as Fermion modes, or that we trace quantum field theory, that we write quantum field theory in a way that it's intrinsically finite, or that we replace it with something that is finite. All right, the next topic, following the Blasio rule, is, I want to do now the Feynman propagator. We've already done the Feynman propagator for boson for spin 0 and spin 1. I now want to do it for spin 1/2, and so let me start out with that. First of all, what is the field? The field is psi of x. It's an integral d cubed p, 2 pi cubed, square root 2 omega p, and then of course 8ps, u of p and s, e to the minus psi px plus d dagger p and s, v of p and s, e to the I px. So that's the field, and what we're going to look at is the Feynman propagator course is the mean value in the vacuum of the time ordered product of psi with psi bar. And the first thing is, let me write down what that will be, and in fact, let me write it down in a simple form. It's, first of all, let me put in the t, time ordered product, psi of 0, psi bar of x. This is the thing that I'm going to compute, basically following Schwartz here. So this is going to be theta of minus t, certainly, times 0 psi of 0 psi bar of x. And then we're going to actually put in a minus sign here. Theta of t and this minus sign is needed because we want this to be a smooth function when t crosses 0. So for negative time, the psi bar is on the right. For positive time, psi bar is on the left. But when psi crosses, when you anti-commute two fermions, you get an extra minus sign. This thing compensates for that minus sign. So that's the point. Okay. And so the first thing we're going to do is we're going to compute, let us say, the first term. Any questions? 0, psi of 0, psi bar of x, 0. So this is an integral d cubed p d cubed q. And I'm going to be deviating a little bit from Schwartz here, so you want to watch me like a flock of hawks. Well, I guess hawks don't flock.
I hope not. It'd be terrifying.
What?
That'd be terrifying, a flock of hawks. They would like take down people.
Yeah, I guess it would.
We could
It's
watch
like-
like a flock of seagulls.
Flock of eagles? Do eagles?
Seagulls.
Seagulls. Actually, not the last time I was on stage, the time before that I was in Washington at NIH. God, there was a lot of peace. And in fact, there was, opposite NIH, there's a huge military hospital, which has been developed. Walter Reed used to be in downtown Washington in the naval hospital was opposite NIH, and they decided that the area around Walter Reed was too seedy, so they moved Walter Reed to a naval place, and now we've got a huge place. Anyway, when I was there, typically in whatever the season was that the geese were going north or south, I don't know what they were doing, I didn't ask them, and they didn't tell me, but it would be 30 or so geese just on the lawn, and nobody paid any attention to them. Sometimes actually there were deer going across the lawn, and nobody pays attention to them, although some of the military men at the hospital who are hunters, they sort of drool looking out the windows at the deer. I guess the geese also. These geese were huge birds, I mean, yay bigger, so. And, well, anyway, nothing to do with science, so let me go on with this. I don't know why is there any connection here? Probably not. All right. Vacuum. What do we do? Well, we first of all have the term from, one of the advantages of using zero is that the phase factors go away. And so what we have is something much simpler. We have just A of P and S, U of P and S, plus B dagger of P and S, B of P and S. The next term, though, is a dagger of Q and S prime, U bar of Q and S prime. E to the I Q X plus B of Q and S prime, B bar of Q and S prime, e to the minus I Q X, right bracket, vacuum. I hope you all are eyesight like eagles or hawks or something. Well, there are four terms there. But the B term doesn't contribute here, and the B dagger term doesn't contribute there. And so all we get is integral dqp dqq 2 pi to the 6th square root of 2 omega p 2 omega q sum S prime U of P and S bar of Q and S prime 0 A of P and S a dagger Q and S prime E to the I Q X. And once again, Dirac saves us because this anti-commutation relation will give us delta P minus Q, delta S minus S prime if you want, 2 pi cubed. And so what we get from this then is something fairly simple. It's dqp 2 pi cubed 1 over 2 omega p sum of over S U of P and S bar of P and S e to the I T X. So, and this U bar, you remember, is that famous sum that is, in fact, I could write it down right now. It's dqp 2 pi cubed 1 over 2 omega p, and this sum over S is p slash plus m e to the I px. All right. So that was a vacuum psi of 0, psi bar of x. Now what we want to do is compute the other one. And the other one is 0 plus psi bar of x, psi of 0. And so this will be a sum over S and S prime, integral dqp cubed d cubed q 2 pi q 1 over square root of 2 omega p 2 omega q. And now this will be, well, I left out the vacuum state, so let me put it there. Vacuum v of q and s prime, v bar of q and s prime, e to the minus I qx. There's an a dagger term, but the a dagger on the left isn't going to matter, so I'm going to drop that one out. I won't even bother to write it down. And then the next one is b dagger, and in fact there's an a term that I'm going to leave out also. So it's b dagger of p and s, v of p and s. And now, once again, b dagger gives us delta cubed of q minus p, a 2 pi cube, as delta of the spin indices. And so this gives us an integral sum over s, integral d cubed p, 2 pi cubed, 1 over 2 omega p, e to the minus I px. And now, what we would have would be, I'm a little puzzled here that we've got v bar v. Because I want to write this as v bar. All right, well, let me write it the way it is at the moment. V bar of q of p. Right, v bar is on the left. V of p and s. Okay, but now if we put in indices, say we have, say, an I there and a j there, then that would be an I here and a j there. And all right, this is something when I was doing this afternoon, I didn't notice. Well, let's see what we've got, because if that was an I, maybe that'll do it. Let's let us start out by saying there's an I here and a j there. So putting in the i's and j's, we would have an I here and a j there, and that would have given us I, j. But now, you see, this is I, j, and so here we're really dealing with j, I. And so consequently, this is j, I. And so now, if we write this whole thing as a matrix with the i's on the left, this is then integral d cubed p 2 pi q 1 over 2 omega p and e to the minus I px, and then sum over spin v of p and s, v bar of p and s. And so this is integral d cubed p 2 pi q e to the minus I px 2 omega p. And you don't have my spinner notes here, do you? No. Anybody? Using this toilet paper.
We don't print them out.
What?
We don't print them out.
Oh. Okay. What I have here in my notes is p slash minus m. And I'm just wondering, is it p slash minus m or is it m minus p slash? So let me see if I get my notes out here. Ah, I brought them with me. So, because the trouble is, I didn't do that one explicitly. Yeah, I have P slash minus M. Is that what I wrote down? Yeah, okay. All right, so that's that. Now we have to put these two together with the, we have to put these together with the theta functions and see what turns out. And let me try to get some of the chalk off this thing. Okay. All right, so what we have then is time-ordered product. Actually, let me just use square brackets because those brackets that I wrote there give the impression that we're doing an annual commutator. So let me just say sine of 0, sine bar of x. Okay, so what is this? This is theta of minus t times 0 psi of 0 psi bar of x 0, and then minus theta of t 0 psi bar of x psi of 0 0. Okay. And so this is going to be theta of minus t times an integral d cubed p 2 pi cubed 1 over 2 omega p. And I'm going to write this as e to the I omega pt minus p dot x. I'm going to make this very explicit. And then we're going to have, maybe I should make this explicit also. This is p slash plus m, so it's omega p gamma 0 minus p dot gamma plus m. So that's the first term. Then the next term is minus theta of t, and now dqp 2 pi cubed 2 omega p. And now we have e to the minus I omega pt, and then plus p dot x. And then we have p slash plus m, but this is really omega p gamma 0 minus p dot gamma minus m. Okay, so as I said, I'm doing this differently from Schwartz. Schwartz takes advantage of the derivative quite early, but then I don't know, I was a little bothered with the way he did it, so I'm going to do it this way, which I think is a little bit safer. Now, there are a couple of identities here. Theta of minus t, e to the I omega pt. This turns out to be a contour integral, I over pi integral, and I'm going to call this e to the I p0t, dp0. That's p0, not Pizarro. Divided by omega minus, well, there I screwed up, p0 minus omega p minus I epsilon. And then we have this thing, theta of t e to the minus I omega pt. And this is minus I over pi integral e to the I p0t dp0 over p0 minus omega p plus I epsilon. Okay. You guys don't want me to derive the contour integrals again, do you? All right, now let's put these two things together. So the first term then is integral dqp 2 pi cubed 1 over 2 omega p. In fact, both terms have that. And this one has, well, first of all, it has the phase factor, which is, well, just e to the minus p dot x, because I'm going to absorb the phase factor with the theta, and that's going to give me this, I over pi integral e to the I p0t dp0 divided by p0 minus omega p minus I epsilon. And now that's multiplied by omega p gamma 0 minus p dot gamma plus m. Okay, and now we can add in the second term, and maybe I'll do it this way. Integral dqp pi cubed 1 over 2 omega p is an e to the I p dot x, so the phase is different there. And now we have minus theta of t e to the minus I px, omega pt. That's this thing apart from a minus sign, but if we put a minus sign here, we make a plus sign there. So minus theta times the phase factor is this thing. And so now we have I over pi integral e to the I p0t dp0 over p0 minus omega p plus I epsilon. All right, I think I've got everything straight now. Oh, except for this last factor. And so I'm going to go on to this board. Okay, so this last factor is omega p gamma 0 minus p dot gamma minus m. All right. So anybody see any minus, any screw up, everything kosher? All right. Now we want to combine these things. And okay, so first of all, I want to get everything the same except for these funny denominators. And the way to do that is, first of all, we're going to have to flip p. If we flip p, the omega p doesn't care, the omega p doesn't care, the p0 doesn't care, the p0 doesn't care. None of these guys care, but there's going to be a plus sign here. Okay. So, if we do that, what we get is integral d cubed p 2 pi cubed e to the minus I p dot x 2 omega p okay, we have the I over pi out in front, so I can factor that out. We also have e to the I p0t, so that's comforting. And then we have a dp0, so we have d, so everything there looks fine, but what we've got now is, and let me try to keep all this straight here. We've got omega p gamma 0 minus p dot gamma plus m over p0 minus omega p minus I epsilon. So that's that. And then this one is, so let me keep track of this. We flipped the sign of p vector, and so what we have here is omega p gamma 0 plus p dot gamma minus m over p0 minus omega p plus I epsilon. Is that right? Okay, now
Can you combine the d cube p with the d0p?
say that again.
You can, no? You can't. Can you combine the exponents?
Yeah, I want to combine these things,
Oh,
but I'm not quite sure how. So, all right, let's, one term is 1 over omega p, or 2 omega p if you want. And it's, well, that term, the omegas just cancel. And so there's a, the gamma 0, I guess we'll have to do these separately. The gamma 0 term is 1 over p0 minus omega p minus I epsilon plus 1 over p0 minus omega p plus I epsilon. And so this is gamma 0. Now, is this the complex conjugate of that? No, it's not. So instead, I'll just multiply through by p0 minus omega p. Well, so then it's p0 plus omega p. And then we have here p0 minus omega p minus I epsilon times p0 minus omega p plus I epsilon. That's one term, but then the other term is plus p0 minus omega p. Okay, so the omega p cancels from the numerator there. And what we have for the gamma 0 term then is gamma 0 p0, or 2p0, and then the denominator is,
Would it be easier? If that second term is factor out the minus sign, then you would have p0 plus omega p minus I omega. I mean, minus I epsilon.
Marvelous suggestion, because now these are the same terms, and so this is p0 squared minus omega p minus I epsilon squared, and effectively then this is 2 gamma 0 p0 over p0 squared, and now this thing is minus p vector squared minus m squared, and then the overall term is plus I epsilon, because the I epsilon is multiplied by p0 squared times omega p, and both of them are positive. Okay, so that term gave us that. And now there's the other term. And this is exactly what we want from this term, because it's gamma 0 p0 over the usual Feynman denominator. The other term, though, is 1 over omega p, and it's m minus p dot gamma. We're running out of time. All right, I think maybe I should do the rest of this at the beginning of the hour next time. Who made the great suggestion? You?
Yeah, I believe it.
Oh, you get 2. Good. Any questions? All right, so let's